All right, well, I'm super excited to be here, and I wanted to start out with a really simple thing, which is why we love containers. And I think this goes back, for me, quite a long way. It's really because, believe it or not, there was a time before virtual machines when you actually had to write internet applications directly on Unix processes. So kind of my first wave of writing internet applications, which was right 94 or so, 20 years ago, it was actually in some ways more like Docker than the intervening period has been. And that's that it was very application-centric and a little bit more focused around the processes and groups of processes. So we just find that very natural and productive. I'd also say that it is the way Google works internally, and so it's very similar, both the actual container image, but also the use of Linux containers. We use signed static bundles, which are frankly not as nice as Docker, but they're trying to get the same idea of repeatability and early binding of dependencies. So that's a very natural fit for us. So, you know, I kind of wish we had done Docker images the way Docker did them, but that's okay. They did them. But Linux containers we did do a lot about, and I'll talk about that as we go. But I would say we really do run everything in containers. So this was announced a couple weeks ago that we launch about 2 billion containers per week. And we actually have containers inside containers. Our VMs run inside containers. We'll have containers inside VMs inside containers. Now, I would say that the kind of half the reason I'm here is that we didn't just use containers and it was all easy. It took us a decade of using containers to actually figure out what it is they should do. And so we kind of evolved to our use of containers. And in fact, I kind of feel like it's been a little lonely the last few years using containers in a way. But Docker has fixed that, making it exciting and in particular much easier to use. And we kind of feel like this excitement is about something real, and we need to both leverage it and contribute to it. So I'm going to cover a few problems with containers that we dealt with. Let's start with the easy one. The first problem really is that containers interfere with each other. They are not naturally partitioned. They'll interfere on many different dimensions. And so we want them to be both prioritized correctly, but also to just be fair, right? If we have 3 things, we do normally expect them to get about a third of the resources each. Well, what happens when one of them goes crazy? Can it take out the other 2? Without a little bit of help, the answer is yes. Bad things will happen. So we did a whole bunch of open source solutions over the last 10 years. I'm not going to go through these in any great detail, but I would say the pattern here is that we started with CPUs. We got those with CPU sets kind of working. It was a little clunky. Did some memory partitioning by lying about NUMA, which is awkward. C groups was a generalization that got us different kinds of hierarchies, added support for all kinds of other resources, such as bandwidth and QoS, and finally revisited memory, doing it more seriously, where you're really trying to account and allocate all the use of memory, including kernel memory, and actually enforce the correct usage. So if you put all these things together, I would say the tools are there to get decent isolation. Right? But you actually have to use them, and they need to be part of the entire container system you're using. So as we move towards lid container, all these things have to be correctly folded in there. And that, I think, will happen. Second problem is once you start partitioning your resources, because you have got your great container isolation, your utilization goes down. And I would say, having watched many cloud workloads, I would say most users on the cloud have relatively low utilization. And at first attempt, using containers will actually make that worse because you're giving resources to a container and nothing else can use those resources. Right, so to fix that, we want to actually make the Slack resources available to other containers, right? Utilization goes up, it's basically you get more out of your VMs. So we do this internally based on kind of this principle of tier 1 and tier 2. So tier 1 is the things that are live services, like a search engine, and you provision resources for those based on peak load. Now, that's a problem for lots of reasons, but the root problem is that peak load is much higher than average, which means if you give the resources to your containers that they need for peak load, you're going to waste a lot of resources. right? So it's very important to have some way to make use of them when they're otherwise idle. And so tier 2 is the kind of the set of services that take advantage of all the Slack resources that you're not using when you're not in the peak load. And the classic example for us was MapReduce. The reason we could do giant MapReduce, I would actually argue the reason you can do big data in general is that there's a huge amount of Slack resources in these systems, right? So the computing is free, basically, to do MapReduce, given the difference between peak and average load. So now we really want the containers to provide this kind of isolation, right? So it's one thing to do this at the fleet. Even on a VM level, you really would like to support this kind of differentiation among your containers. So the short answer is, if you use the tools we have, including the ones I already mentioned, like C groups, if you use them correctly, you can get these two kinds of mixed workloads to work on the same VM quite well. But you have to think about it this way. I'll say as a side note that when we run your VM as a cloud customer inside a container, we don't actually then run MapReduce in your VM when you're not using it, right? So we actually do give you 100% of your container. But for our internal workloads, it's very important to be able to take back the Slack resources. And I would argue in your own apps deployed in the cloud, you will also want to take back your Slack resources for the VMs you're paying for. There's no reason not to use all your VMs all the time. And containers are going to make it much easier to do. Third problem is it turns out it's actually hard to enforce isolation. And this is a somewhat subtle problem that we really didn't deal with until about 2010, 2011. The normal way this happens is you have a kind of big control loop where the way you enforce isolation for some things, like for a while memory, is you can see how much memory or disk something is using, read the stats. You then basically verify that the allocation of those resources match what you expected. And if it doesn't, then you have to make some adjustments. So because this is a loop, it's kind of slow, right? You read some periodic thing, typically at user level, and then you make adjustments, and you kind of have a mediocre control system driving your resource isolation. So we made a lot of work on trying to get direct enforcement in the kernel, meaning that you should say what the resource allocation should be, and we should put that enforcement in the kernel. It might still be a loop, by the way, but it's a tight loop inside the kernel that's reliable and fast. This is roughly similar to why you want, in general, TCP to be in the kernel and not in user level, because if it's in the kernel, there's a control loop that does your window sizing that works very well, because the whole control loop is inside the kernel. This is the same kind of problem. We really want control loops, if we have to have them, to be inside the kernel where we can enforce it directly no matter what's going on at user level. Now, so the status of this is it's pretty good, right? There's lots of enforcement in the kernel now for different kinds. It's not perfect. Caching, in particular, memory bandwidth are resources that are not isolated among different containers, so they can still cause interference. I'd also mention as a side point that these kinds of changes, historically, we've had trouble getting accepted upstream. And one reason for that, which I think is important to mention here, is that upstream in general has not understood why we wanted to do these weird things with containers. All right, so subtly, Docker is actually helping us by saying, hey, containers are great and important, and they're changing the overall community's view on why you might want to do some of these patches. So thank you for that. And finally, because I said there is still interference sometimes, it's worth pointing out we actually published some work on how do you make adjustments when you detect interference. And it turns out we can detect interference by looking at the cycles per instruction for an application. We know what it should be because we've run it before, and if it's running slower than it should be, it's probably because something else is interfering with it. Right? So that's actually outside the container system. It's one of those bad control loops I just mentioned, but it's kind of a catch-all, meaning we can detect interference through slowing of applications, and then we'll move them. We'll migrate them to other VMs where hopefully they won't have similar interference. Well, that's in a paper. You can read about how we do that. Now, those are just kinds of things I want the community to think about of when you get serious about containers, you want to address these issues. But there's one more, which is kind of a meta point, which is that everything so far I've talked about is essentially knobs and a very wide, complicated API to control all the things you want to control about your containers. And that was causing us quite a bit of problem, because every time you change the kernel or make changes to anything really, this wide API between containers and the kernel has to be adjusted. And so to get around this, we released something in 2013 called Let Me Contain That For You, or the smooth rolling LMCTFY, LMCTFY, depending on how you pronounce it, is really exactly this. It is a declarative API for containers that say, these are the resources I want to have for each of my containers. It handles nesting, it handles prioritization, so you can do tier 1 and tier 2 kinds of workload mixing, and includes the enforcement of those things. And I think the long-term importance of it, and why we want to move it into libcontainer as functionality, is that it's a stable declarative API for what you want your resources to be, right? And we've really found that that is a super important model. Now, these are all pieces of what you need, I think, to use containers effectively. And since we believe that they are kind of the right way to do these things, we really believe that the open source containers based on Docker are the foundation that we want to use. And so we're kind of contributing these, both the ideas and the code, as things we think real, stable, long-term foundational containers have to do. They have to have a clean API like this. They have to support nesting and prioritization of resources. They have to have a stable API. So we've already done quite a few things with libcontainer to try to make it easier to use, the LMCTFY kinds of things. But in general, that's ongoing work. And we'd like to move all this functionality into libcontainer over time. Finally, today we're actually releasing something called CAdvisor. We actually released it a little bit early for the Docker Hackathon. It's a small thing, but it's kind of nice. It basically tells you, for all your containers, what is their instantaneous resource usage and their historical resource usage. So instead of knowing how much memory your machine is using, you can actually say, well, here's how much is my MySQL container using, differentiated from my logging container, differentiated from my web server container. Right? Get all those things in a nice, fine, granular fashion, so that it's very clear how it is that your resources are being used. Now, the way we use containers is not really ever as a single container. We really use them as groups of nested containers, which we're going to call pods. And LMCTFY gives us the nesting support we need and the isolation and utilization. And we found this because really the group is actually the thing that we want to manage, right? In particular, many things we end up breaking out as helpers. In fact, many people have been talking about microservices. This is essentially a tool for microservices, right? We really want the logging system to be a separate service in the same group, right? Because it's logging the things in its group. It makes content management for distributing your web content with your web server. Those are two things in the same group. And they shouldn't have the same priority, right? We don't want the logging system to break the web server, right? So we really want isolation, but we also want the utilization, so that if the web server doesn't have full load, it's a good time to do log rotation. It will just happen naturally given the prioritization. I'm missing a. There we go. Now, what are the attributes I want a pod to have? There's quite a few, and I don't think they're rocket science, but this is, again, how we think about it. The first and most important thing is a pod is a group of containers that's deployed together. And that means, by the way, that if something dies or the machine is having problems, we're going to move the whole group, right? The groups are always co-located. We use shared local volumes. That's both as a communication mechanism among the members of the container, members of the pod. That needs to be a first-class thing. It's not quite there yet, but that's fixable. And this one that's a little forward-looking, individual IP address per pod. And this is one that's, I think, a little subtle. What it means is that the ports that you allocate for your pod, you know they'll be free, right? Because nothing else is going to be on your VM using that port number, because even if it's on your VM, it doesn't have the same IP address that you have. Right. So this is a subtle one, and it's a lie a little bit, actually. We don't do this. I tell you this because this is what we should have done. Because if you do pods this way with one IP address per pod, You do not need to allocate ports at the last minute. Right? If you have more pods per IP address, then you don't know what ports are available till you actually know who you're co-deployed with. Right? And that means you actually have to late bind the port decisions, and you have to distribute the decisions you made out to others so they know what ports to use. And you can see the port munging in all the different various tools that sit on top of Docker, passing ports around. Right? So here's an idea, really, gem of the idea for the community is if you use a pod model, and if you say, I'm going to have an IP address per pod, then you can know at build time what your ports are going to be. Right? And it's very easy to distribute them and to synchronize on them. Right? So not what we did internally at Google, something we regret. You don't have to make that mistake. Now, we're releasing something called Kubernetes today. It is yet another orchestration thing that sits on top. That is not a bad thing, as Solomon said. There are many of them because it's an exciting and important area, and an area where we need to get agreement. And I'm not going to give a demo, sadly. I only have 25 minutes, most of which is gone. But Craig and Brendan are going to actually go through that later today at 2 o'clock. You can go see that session. Now, the reason to do an open source release right now in this space is because it's about the ideas. So I'm going to talk a little bit about some of the ideas in it, and then you can get the details from Brendan and Craig. We obviously we're doing orchestrations. We want to have a manager that's going to have an API for managing the cluster. It's going to have replicas. It's going to manage replicas, which it tracks with etcd, which I see many other systems are using, or Zookeeper. That could have been used as well. Then you're going to have your K-workers. Workers are replicated Docker images. One subtlety here that I think is worth mentioning is that we use parameterized containers. You can think of them as containers that have arguments. I've seen other people use this pattern, but I think we should actually call it out as something we should make a first-class thing. We do it by basically installing environment variables in the container so that the container can understand what its parameters are. It's kind of like having, argc and argv. And then lastly, it has a shared view of what a load balanced service is, and I'll talk about that in a minute. Now, because it's about ideas, let's talk about 2 ideas I think are worth getting across from this code. And you can play with this. It's actually out now. So one idea is that we define services using something called labels. And a label is really very simple. It's just a key value pair, typically just a name at the moment. And you could have many labels, but in particular, they are overlapping. So it's not like you have a static hierarchy of groups, and this is your replica group. Your groups are defined instead by a query, right? So if I want to know what are my servers that are running Redis, that is actually determined dynamically using a query. And all the running containers that are labeled Redis are in the Redis group, and that's what you'll get as your set of replicas. And it's important that it's a dynamic query because the set's going to change whether you like it to or not. Right? So instead of having a group and trying to maintain that group, we flip it around. Say, here's the set of things that are running. They are by definition the group. Right? That is the truth. Right? And then you do the label query to tell you actually what is the current membership. That's a very useful pattern given that things break. The way you define a service, then, is it's just a load-balanced replica set. So on the right, you can see a service definition. This is an actual Kubernetes service definition. It gives you the name of the service, the port it runs on. I'll talk about that in a minute. And then the name. And the name here is essentially the query you issue to find all of the members of that set. So it's going to load balance against all the containers that have that label. And if you add container, it will discover that, and it will start load balancing that to the new container automatically. Right? So you don't tell the master detects. Right? That's a much more stable pattern. Now, the way you actually access your service is by a local port. Right? So when I say this has this port 10,001, I know I can use that statically because I have the single IP address thing I just talked about. And that port on every container is going to go to this service. So it's kind of solving the naming problem in a subtle way. Your namespace is now the ports. The port for 10,001 goes to that service on all your containers, and then you don't have to actually discover it. It's known to you. And the way that works is by having a load balancing proxy on every node that's forwarding your traffic to the place it should go. Now, the second idea that's in this that's worth talking about is the reconciler model. And the idea here, it goes back to the declarative thing, right? We believe that you should say what you want, and then we'll work to make that true. So in particular, we're going to declare the desired state of how many replicas we want, and we run the reconciler loop, which is basically a loop that says, query the actual state of the system, see if it matches the desired state, and then reconcile it if it doesn't. So if I have too many, I might kill one. If I have too few, I might add one. Now, it's maybe obvious, but it's worth saying because I don't see it in all the projects on Docker. I think this is a pattern we should adopt, which is that having an explicit desired state is a good idea, right? In particular, otherwise you can't tell if it's askew, if it's askew because the desire changed, meaning you decided you wanted to have more replicas, or because something bad happened and the actual state doesn't match, right? So we're going to have a model where the desired state is always clear. You can change it if you change your desires. But the actual state is something that is actual, right? It can get screwed up at times. And therefore, we reconcile the actual state to the desired state as a kind of ongoing, recurring pattern. So in Kubernetes, you just say, I would desire to have 2 replicas, and the master will keep you at 2 replicas. If you want to use other systems, they say, oh, I'm going to have my loads going up. I actually want to have 3 replicas. You can make that decision, but that's a change in your desire. You can dynamically say, I'm going to change my desire, and then it'll adjust to that. So finally, we're trying to get to robust containers. So there's a lot of things that go into that. Obviously, Docker used well gives you clean, repeatable images. That's fantastic. From single nodes, we're seeing patterns like allocating ports per pod, conflict-free because of the IP address. We use things like data-only containers and shared volumes, making the shared volume a first-class abstraction. Parameterized containers to make it easy to have pass-in variables and arguments really to your containers. At the multi-node level, we're really looking at labels for time-varying overlapping sets. By the way, that means it's very easy to do load balancing among just your canary Redis servers, and that will not include your production Redis servers, right? That's just a change in label query, right? So you can have as many canaries with different labels as you want, and they're all dynamically found. You can make up your own labels. You can say, oh, I want Dave's Redis service because I made some change to it, and now it'll only load balance across that. Right? So it's very flexible that way. And finally, the reconciler model, which we use actually at multiple levels. We use it at the worker level to make things run well, including things like resource setting, but also at the master level. And finally, I think the long-term excitement for me is that, like I said, in some ways it's back to thinking about processes first, but it's really that these are good building blocks for cloud native. So I mentioned some of the things that I think make a pod a good building block. Ones I haven't mentioned that are I think, self-evident, but very handy, things like auto restart. So there is no supervisor daemon running. If you start a Kubernetes service, it will restart those nodes automatically. That's part of reconciliation. There's liveness pros. There's the stats for load balancing. So those just get built in and exposed. Things like SSHD is part of your environment. It's not part of your container. Right? That's something we have been doing for a long time. And there's a little further out things that I think are worth talking about that I would say are good places for agreement in the community. How do we notify containers of events? I think an important part of being cloud native is that your containers get events directly, like I'm going to move you, or we want to start and stop you. So that really shouldn't be a boot time service thing. It really ought to be part of what your hosting framework provides directly. But that's a place where there ought to be agreement on what actually it means. And there's other things that actually are a little unclean now, like how is it that you do an out-of-memory notification to a group of containers and make sure that we can kill the right thing, or we can return memory before something gets killed unintentionally. So there's a bunch of places there where we can do, I think, quite a nice bit of work. And we've certainly found the labels and reconciliation to be good things as models for kind of a cloud-native path forward. So finally, we are standardizing around the Docker container image. There'll be some more announcements on that today. I'm not going to go through them in detail, but I'm happy about them. We do believe in open containers, and we think they have to have the full feature set that we've seen required over the last 10 years. They have to have isolation right, they have to have nesting, they have to help you with utilization, and they have to help you with enforcement. Right? All those things are not really negotiable. Right? That's what you need to run containers at scale and get the most out of them. We've been moving to Go, actually, on things like the CAdvisor thing I mentioned. This for stats is actually written in Go. That's with the hope that it'll make it easier to integrate with libcontainer, although now I know there's a C version as well, which is going to work very well for us. But we'll be flexible on language. So the news today, Kubernetes, you'll see that at 2 o'clock. Docker on GAE, a lot of things to make it easier to use Docker on Google App Engine. That's not the title of Kate's talk because we had to give a generic title long ago, but that's at 2:50 today. And then CAdvisor, which is a little bit smaller, just a tool for stats for your containers. And thanks to Docker, right? This is an exciting time. I think we are on the verge of something that's a major shift, and I really look forward to making a great space together with all of you. Thank you so much.